In this video, I'll show how I made a magnetic levitator that can float up to 3 pounds. Its strength comes from having such a huge electromagnet. The core weighs 7 pounds, and 3 pounds of 16-gauge magnet wire is wound around it. The core is built from a 2 by 6 inch solid steel cylinder with washers welded to the top end. The washers increase the strength of the magnetic field by a little bit and also serve as mounting flanges. After welding the washers to the core, I wound the 16-gauge wire on my old Tesla coil winding fixture. The result was a little sloppy, but it'll definitely work. The magnet weighs in at 10 pounds and has a pretty impressive amount of pull. Here's it connected directly to an 18-volt battery. I also did several tests at different currents to see how far up it would float a big 40mm N52 magnet. So the electromagnet obviously works pretty well. Now I needed some kind of structure to mount it in. I designed this fully 3D printed fixture that was made to look like a monolithic object, which really was total overkill because it could have just been built with some 2x4s. The total height of the fixture was 16 inches, so I had to print it in multiple pieces and glue them together. Both my printers had to run over 24-hour jobs to finish the parts. I think this would have been better off being done with plywood on a laser cutter. On an attraction-type levitator, the Hall effect sensor sits on the end of the electromagnet. However, with magnets as strong as I'm using, it could easily be crushed if a magnet comes too close and snaps to the steel. To protect the sensor from impact, I printed a 1/4 inch thick disc that it would be recessed inside of. The electromagnet itself just drops into position in the fixture and its weight holds it in place. Now that the heavy lifting is done, I need to build the circuit. No microcontroller is necessary for this circuit. Everything is controlled by analog signals. The 10 millihenry coil is the electromagnet, and it's controlled by a low-side MOSFET that has its gate driven from the output of an LM324 op-amp. The negative input of the op-amp is supplied by the Hall effect sensor, and the positive input is a reference voltage that's manually tuned by a potentiometer. A 100 nanofarad capacitor is placed on the sensor leads to remove any noise, and a linear regulator provides the 5 volts needed by the sensor. The input has a large choke and capacitor bank to smooth out the big current swings. As with any inductive load, a flyback diode is used for protection. In this case, a very large diode is needed to handle the coil's high currents. Finally, a status LED is connected in parallel with the electromagnet. This is useful when you're manually tuning the reference voltage to see when the MOSFET turns on. Here's a look at the op-amp logic on a breadboard. I have my tuning potentiometer, a status LED, an LM324, and a Hall sensor. When the magnet is far away from the Hall sensor, the LED is on, meaning the op-amp output is high. When the magnet gets close, the LED turns off. This logic makes sense because if the permanent magnet was too far away, the electromagnet would be turned on to attract it, but when the permanent magnet comes too close, you'd want the electromagnet to shut off. So here's what the finished board looks like, and it fits perfectly inside the lower compartment of the levitator fixture. And here's the full assembly. The board is still exposed so that I have access to the tuning potentiometer. Alright, let's do a first test. The magnet is surprisingly stable once the reference voltage is dialed in right. I was pretty surprised how much disturbance it would tolerate and continue to float. There's no mechanical friction, so if you set it spinning, it will pretty much go forever. The only thing slowing it down is an extremely tiny amount of aerodynamic drag. The power consumption is also extremely low. A little over 1 watt is typical for my small magnet, but even if I use my larger magnet with a 2 to 3 pound load on it, it never went above 6 watts. This seems to be because the magnet is sitting just barely outside the region where its attraction to the steel core would overcome gravity, so just a tiny extra pull is needed to make it float. I should also point out that the limiting factor on the levitation range isn't the electromagnet's power, but the resolution of the Hall effect sensor. As I showed earlier, the electromagnet can act over very large distances, With enough current, I could actually get it to attract magnets from over a foot away. But at about 2 inches of distance from the magnet, the Hall effect sensor signal is indistinguishable from its idle state, so I need a more sensitive sensor to float further away. Okay, back to the circuit. Let's see what the op-amp output looks like while we're floating a magnet. What we're looking at here is the gate voltage on the MOSFET controlling the coil. When there's no magnet present, there seems to be about a 50% duty cycle square wave on the gate voltage. This is because when the electromagnet turns on, after a few milliseconds, the field becomes strong enough to trip the Hall effect sensor, shutting it off again, and then the cycle repeats. When a permanent magnet is brought within range of the electromagnet, the duty cycle drops to around 5 to 10% at around 300 Hz, so the circuit is making corrections about 300 times per second. Alright, let's cover up the board to protect it from falling magnets and try some more stuff. Here's a much bigger magnet. This is two 40 by 20 mm N52s stacked together. This thing has a pull of more than 100 pounds when it's stuck to a piece of steel, so it can be very dangerous to handle. On the levitator, though, it's much more stable than the smaller magnet. One of the most entertaining things about floating objects in midair is making them spin without friction. Here's a tiny windmill I attached to a magnet. When I gently blow on one side, it starts spinning really fast and doesn't slow down. I also had a lot of fun floating some of my tools. We're up to almost 3 watts now with the additional weight. This wrench is the biggest thing I floated. It weighs almost 3 pounds. That pushed the power consumption to over 6 watts, amazingly small considering I'm floating several pounds in midair. It's also possible to float ceramic magnets, but since they're much weaker than neodymium, they float closer to the electromagnet. Let's try an experiment with eddy currents. Here I have a big block of aluminum. When I swipe my big magnet over it really fast, the change in field induces large currents in the block that create their own opposing field and act like friction against the magnet. Note that I'm not touching the block with my magnet in this video. When I launch the magnet off the aluminum block, it floats up smoothly because of the damping effect of the induced currents. Whenever I drag the block quickly, the magnet will follow along, but if I hold it in place, it acts like a brake, stabilizing any jitter or oscillation. And the induced currents aren't just repulsive. If I move the block away from the magnet quickly, the magnet will try to chase it, and I can pull it out of the levitator's attraction region. Another fun thing I found I can do is stick big bolts on the magnet and attach steel hex nuts to them while it's floating. The hex nuts will just fly out of your hand toward the bolts. The magnetic bolts are so heavy by comparison that you can add dozens of hex nuts without destabilizing the levitation. And as long as I'm at it, why not levitate a banana? I'm happy to report that the banana didn't taste any different after magnetic suspension. I found that I could make a small improvement to the levitation distance by adding a permanent magnet on the top side of the electromagnet core. Under normal conditions, the magnet is floating at a distance of about 1 3/4 of an inch. With the addition of some N52 magnets on top, at the same power consumption, the distance increases to 2 inches, about a 15% improvement. I imagine I can improve that a lot more with a bigger magnet on top. Now you may have wondered what my channel profile picture is. That's my mascot, Lenny the Pirate. Lenny is a hypercube, also known as a tesseract, and I decided this project provided a good opportunity to make him in 3D. Now I couldn't make a device that floated things in midair without a UFO being involved, so I designed this flying saucer. My big 40mm magnet goes under the dome of the flying saucer, and the two halves snap together with tiny magnets. I also tucked away a pair of AA batteries to provide me 3 volts for the LEDs on the saucer.